on p-Adic mathematical physics and its application. I want to thank to all the people and institutions that have made this conference possible. We will have a big conference, 49 talks covering a large range of topics. All the talks will be available at the YouTube channel of the conference. I invite you to subscribe to this channel. Now I pass the microphone to Professor Kosire, which is the chairman of the session. Welcome to the conference.
Okay. Thank you very much for everybody for coming. So the first speaker of this session and of our conference is Professor Branko Dragovich. Title of the talk is From p-Adics to p-Adic Matter.
Well,
okay, please.
Well, at the beginning, I would like to welcome all participants of this 8th International Conference on p-Adic Mathematical Physics and its applications, which is unfortunately all talks will be online. Of course, it would be better to be together in person and at one place, but the situation is with the viral pandemic requires to stay at home. Nevertheless, it is nice that we can be together online. I would like to remind you that this series of conferences started in 2003 in Steklo Mathematical Institute in Moscow. It was twice in Moscow, also twice in Belgrade, once in Belarus, once in Mexico, and once in Portugal. There was also one similar meeting in Bielefeld, Germany, but with different title. As you know, there is an international journal entitled p-Adic Numbers, Ultrametric Analysis and Applications, and we welcome you to submit your paper to this journal. At the end, I wish you to enjoy this conference and to stay healthy and safe at your home. Now, I am going to give a talk. As you see, the title of my talk is From p-Adic Strings to p-Adic Matter. Here is a plan of my talk. After a short introduction, I will speak about p-Adic strings. In fact, I will give a brief review on p-Adic strings and then of effective field theory for these p-Adic strings. After that, I will speak about how one can get p-Adic matter in Minkowski space from these p-Adic strings with some slight modifications of the effective field theory for p-Adic strings. And then I will consider also this p-Adic matter in a closed universe, and we'll see that all this has sense. And of course, at the end, there will be some short conclusion. So I would like to say that there are many reasons to study p-Adic strings. They have p-Adic valued worksheet. They are also related, as we shall see, to ordinary strings. And they are simpler than ordinary strings. They also have exact Lagrangian. Their dynamics is nonlinear and non-local. And their structure is non-Archimedean, p-Adic, yeah, non-Archimedean, ultrametric. I will give a brief review of basic properties of p-Adic strings. I will also show how matter can be derived from these p-Adic strings, what I call p-Adic matter. And yeah, I will show how we have evolution of some closed universe with this p-Adic matter. Now about p-Adic strings. Let us recall how I introduced ordinary strings. One can start from standard crossing symmetric Veneziano amplitude. It is given by an integral. This is amplitude, this is an integral. X is a real variable. A, B, and also C are related to kinematic variables, momentum. And A plus B plus C has to be equal to unity. So we have here integration over real line. In fact, this is like Euler beta function, but integration is over all real line. So this is called also Gelfand-Graev beta function. After integration, one obtains this expression here, which is symmetric in A, B, and C. And these zeta are Riemann zeta functions. So we have here a well sheet of strings, yeah, which is real, which is parameterized by real variable. So now we can ask a question, what will have if instead of x, which is real here, to put x, which is p-Adic. So we can take an analog of this integral here, which is of the same form. And this x now is p-Adic variable. And A, B, and C are the same as in the previous case. And here we have integration over all p-Adic numbers. So after integration, one obtains this expression here, which is also sorry, with respect to A, B, and C. And this is simpler with respect to this expression here. These are in fact elementary functions. We have, for example, 1 minus p. P is a prime number to a minus 1 over 1 minus p to the power minus a. And also for B and also for C. Now the question is, what does it mean? Can we in some way to connect it with ordinary string? Yes. If we look at this expression here, and if we remind what is definition of the Riemann zeta function using Euler product formula, then one can connect this here with this one. How? Yeah, here we have definition by Euler product formula of Riemann zeta function. We have this product over all primes, 1 over 1 minus p to minus s. S in some real or complex variable where real part is greater than unity. Now from this we see that if we take product of all these p-Adic amplitudes here, yeah, if we take product of all this, we'll get also Riemann zeta functions And it will be just in the same form as here, where nominator and the denominator replace. Yeah. So the product of ordinary Veneziano amplitude with all these all these p-Adic amplitudes is some constant, which is related to the product of the coupling constants for the real and for all these p-Adic. And we suppose that it is constant. So this is a very well-known Freund-Witten product formula. What does it mean here? One can say that, from this we see that amplitudes for the ordinary case and p-Adic cases are on equal footing. Also, one can look at this as an amplitude for Adelic string, where these are various faces of such Adelic string. And what is even more important practically, that this amplitude here, real, for the ordinary strings, which is complicated, can be expressed if we put this on the other on the right side, which is then a product of the inverses of p-Adic of the p-Adic amplitudes. What's also very important that that there is an effective field theory approach to p-Adic strings. In fact, there is a Lagrangian which contains these two terms. This is kinetic term in some way, and has derivatives up to infinity. So this is a non-local term. We have not, it means non-local here, kinematics. And here this term is related to the potential, and the potential is non-linear. What's important that if we use usual procedure of the quantum field theory to calculate amplitudes, then we can get the same amplitude for p-Adic strings, which are here, at this place here. So we don't use this this integral formula, but get this expression for p-Adic strings. And not only for 4-point scattering amplitudes, but for also all higher ones. And not only there is not only Lagrangian in this approach for the open strings, but there are also similar for the closed p-Adic strings. Here are bosonic strings, okay, and these strings also have tachyon. Yeah, okay. When we look at this Lagrangian here, what reminds us to p-Adics is this prime number. But we said that p-Adic strings have p-Adic world sheet. The question is, can we see somehow it p-Adic world sheet? If we look carefully at this term here, one can rewrite in the following form here, where we have some integration with respect to the p-Adic variable u. In fact, we use this expression here from the integration with the p-Adic variables, where this expression, here integration is over Q minus ZP. This is additive p-Adic character, and U to the power K square over 2M square, what we had in the previous case. And such integral gives this expression here. So this is here minus P to K square over 2M square. In fact, this K square comes from when we apply D'Alembertian to this expression here. So we have, in fact, in this Lagrangian, we have, or in other words, one can see that there is, in some hidden way, there is well sheet. For this Lagrangian, effective Lagrangian, one can look for a potential. Potential has this form here, 5 squared minus 5 to P plus 1. This is one factor here. Yeah? And if we present it at the, at the figures to here are for 2-Adic and for example 3-Adic case, then what we can see that there is one local minimum, one local maximum for 2-Adic case, and that we have two local maxima, one local minimum for 3-Adic, and not only for 3-Adic, but also for higher p-Adic cases. Yeah, and now we can look also for the equation of motion, which comes from this, from the previous Lagrangian. Yeah? And it has this form here, P2 minus the D'Alembertian over 2M square, which acts to the 5, and here is 5 to power P. It is easily to see that there are trivial solutions, 0 and +1, and also -1 when P is different from 2. In fact, these trivial solutions just correspond to these local minima, local maximums. And there are also non-trivial solutions. One can use this identity formula, and applying this, one can obtain non-trivial solution along any spatial direction. It will be in this form here, which is like solitonic soliton. And also along time, we'll have the same form, just a different sign in this place here. And also I can take product of all these solutions and get for x square solution x square, where it is for the d-dimensional space-time. A few words about the connection of this Lagrangian with the ordinary string. Let me to mention that if we use limit when p, which is 2 or any prime number, or even one can take any positive integer. One can also take that p prime number p as a parameter, in fact, here tends to unity. And then one can take, one can obtain this Lagrangian here, which in fact is for the ordinary bosonic string in boundary string field theory. Also, Wilson with his collaborator several papers, this one last of these papers, where they also considered the limit, this limit, and obtained the interesting formula. I would like also to mention that one can demonstrate tachyon condensation for the ordinary strings using this Lagrangian, the previous Lagrangian for p-Adic strings. And also there are papers in the last few years which are related to the anti-de Sitter conformal field theory correspondence. And we can conclude from this and from some other cases that that p-Adic strings are similar in some sense and are in some sense related to the ordinary strings. And they are also interesting for this point of view. And they can use as a toy model for the ordinary strings. But I will consider here how we can get some matter where we don't have tachyon starting from these p-Adic strings. So let us look at the same Lagrangian as in the previous place for the p-Adic strings. And let us consider transition here where we have m square, that it goes to minus m square in space-time dimension is equal to 4. And also change sign in the previous case to have a correct sign for the kinetic term. So it means that we change sign at this place here, and also at the end of this Lagrangian, two places we change sign. And then we can look for corresponding potential, which is again similar to that one which we had. But in the previous case, we had that this term is positive and this is negative. And what's the matter of the equation of motion? It's also the same form, but here is now a sign plus, not minus as in the p-Adic strings. Just. So we have this this change of the sign at this place and at this place here. Yeah? What we have now for these potentials? What we have that now they are oriented, these curves are oriented up, not down, they are up. So what was local maximum in the previous case is now local minimum, yeah. And what was local maximum what was the local minimum in the previous case is now local maximum. Okay, and if we look for solutions of this equation of motion, which again I would like to stress now is not here sign minus but plus, yeah, that we'll have again the same trivial solutions, and we'll have again non-trivial solutions where we should just change m squared by minus m squared. Okay, and what I want now to consider is to look for weak field approximation. In fact, to look for a field around this local minima. For let us take this field phi, that it is 1 plus theta, where this theta is much less than unity. Then it means that we apply now in equation of motion this operator here to 1 plus theta, and that it is equal 1 plus theta to the power p, and then we can expand this here, and since this is weak field approximation, we'll get that it is now not non-linear equation, but that it is linear equation, but again with this non-local operator. So we have a non-local equation of motion, which is now linear, because of this weak field approximation. Now the question is there a solution for this, which is non-trivial? Solution of this equation here. The answer is yes, because there is solution of the corresponding Klein-Gordon equation. We take this box minus 2m squared, yeah, and in fact we can take that this theta is of this form here, as in the usual case with the scalar field, and applying this operator here, we get that energy square is equal to m squared. This is matter. This is mass per meter plus k squared, where k is the moment. Now, yeah, it was in what I said here. It was in Minkowski space. Now I want to look what will happen if we put it in some kind of the universe. It means that we have to start with the action for the gravity, where this action is given as in the usual case with as Einstein-Hilbert action. It contains this R, Ricci scalar. Lambda is a cosmological constant, plus action for some matter, and we'll look for matter in this form here, which will in fact be which will incorporate our case with theta field, which we considered just in the previous slide. And what is this function f here? It is in general case, an analytic operator with infinite many these derivatives, and this U of V is related to the potential. Now the Lambertian here is not usual the Lambertian in Minkowski space. Now it is in the more complex case when we have gravity. In fact, this is the Lambert-Beltrami operator. For this section here, with this, one can make corresponding variation, and get equations of motion for gravitational field and this phi field. This is in fact the usual path, and this is which is related to this non-local field phi. And here this omega mu nu is given in this form here, which is also rather complicated, and it is not easy to solve such equations of motion, but fortunately there are some interesting cases, and in our case here, which I will present, when it can be solved. So for this matter field, which is interesting for us, as we presented it in the previous case, it means that here, for p-Adic strings, here it was sign minus, now is plus, and here also we have different signs in front of this term and this one. And already I have shown these potentials. Now they are the same as in the previous case, And what we are interested in now, in the previous case, it was Minkowski. We considered Minkowski solution of this equation of motion in Minkowski space-time. But now we want to consider it in the more general case when we have gravity. So in the case of gravity, we'll consider when the space-time, in fact, we'll apply this to the cosmology where the space is and isotropic. And then metric is given by Friedman, Lemaitre, Robertson, Walker. This expression here, where this A of t is a scale factor, which tell us how we have for the universe expansion or contraction. K, this K here may have three values, 0, +1, -1, which correspond to the flat, closed, or open universe, respectively. In fact, we'll see that we have solution where when, for our case, this K here is +1, it means that we have a closed universe. In the previous slide, it was shown equations of motion, which are rather complicated, but owing to the fact that now we have that the space is homogeneous and isotropic, we have some symmetry. Then we have, in fact, only two independent equations of motion. And usually we take that it is trace of the previous expression for the equations of motion, and also 0,0 component. So we have now these two equations of motion, which we have to solve. But we cannot solve it for the case, in the general case for the field phi, but we'll see that we can solve it in the case when we have weak field approximation for this phi. Yeah, okay. So we have now to look for weak field approximation. In the case when we have that universe is homogeneous and isotropic. In fact, we have to look at this expression here, yeah, for the equation of motion when this theta is much less than unity. In fact, we have weak field approximation. Then we have again this linear equation now with respect to theta. And this D'Alembertian has this form here. Second derivative with respect to cosmic time and first derivative times this h. H is called Hubble parameter, which is first derivative of scale factor over scale factor. So we have to solve this equation here. And in fact, if we present this in, this equation here in explicit form, it is then this equation of the second order and the linear equation. And now it depends on what is this h. If h is constant, we can solve it. This h, Hubble parameter, is constant. If it is of this form, here where a is exponential. So if we take that a has exponential form, then h, this parameter, will be constant. And we can look for solution as in the standard procedure for the previous equation. And in fact, we'll have this equation with respect to lambda. And one can find solutions for this lambda in the simple form plus minus m, and this mass parameter. And the solution in the general case will be here exponential function of minus mt, exponential function of plus mt. So one can also see that there is some connection between this h and the lambda, that if h is positive, lambda is negative. So we have in fact pairs θ1 and a1. When theta has minus here sign, a1 has plus. Let me remind you here that theta is now scalar field, yeah, and a1 is a scale factor. And also we have a similar situation where these signs are opposite for θ2 and a2. Now we can come back to the Einstein-Hilbert action. Now, with respect to this theta field, and if we look at the potential, it will have this form here, which resembles potential for the harmonic oscillator. And just we have now to rewrite the previous equations of motion. We had two equations of motion. Now they will have this form here. According to the solution for this theta field, in fact, this term here and this term here are the same. And so this one is with sign minus, this one with sign plus. So we'll have, it means we'll have simpler this equation here for lambda minus r, r is Ricci scalar. Here one constant, sigma and this alpha, and this omega. Here zero component of the Einstein tensor, and lambda is a cosmological constant, and omega of the previous one expression for the omega. This is a zero component. So we have now to calculate for our case what is r, this Ricci scalar, what is this omega, what is this G00, yeah, and it is given at the next, this next slide. In four-dimensional case, Friedmann-Lemaitre, Robertson-Walker metric, we have that the component R00 is minus 3, the second derivative of the A over A, and here the similar situation for G0 and for R also scale, this Ricci scalar. All is expressed with respect to the scale factor, cosmic scale factor. And now we can calculate this, these quantities here with respect to these two expressions for the scale factor, where this here is sign plus or sign minus. If we calculate it for this one, we'll have 1, 2, yeah, for this indexes 1 and 2. It's minus 3m squared. Then also for this one, we have 2. And the difference you see is only in this sign here minus and here plus. Yeah. And for Ricci scalar, also we have for case 1 and case 2. And again, the difference will be in the sign of this exponential function, like in this for G00. Now, also we can calculate omega, which is rather complicated, but one can calculate it. And we also have two expressions, omega 1 and omega 2. Omega 1 and omega 2 correspond to this A1 and A2. It's here. And omega 00. And we have, for example, here 3p. P is prime number, logarithm of prime number, theta 1. Theta is now this scalar field, and similar situation for the other cases. We can put...
Let me ask you, what is omega mu nu?
Omega mu nu? Omega mu nu, to see what is omega mu nu, we have to come back to the equations of motion. Where is it? Here, you see. When we derive equations of motion for this, for this scalar, for this action here, yeah, then we get this equation of motion here, where this omega mu nu is this this expression here, which is rather complicated, but which is related, in fact, to the non-locality, yeah, to this function f, which is a non-local operator.
In phi.
Sorry?
It's quadratic in phi. It's true.
Quadratic.
In phi, in the field phi.
Yeah, it's quadratic in phi.
Okay.
But we have here the derivatives up to the infinity.
Yes, yes. Thank you.
Okay, so we can go to the almost last slide. If we put what we obtained in the previous slides, these two equations of motion, yeah, then we obtain that they are satisfied. These equations of motions here are satisfied with some connections between parameters. And this connection between parameters are expressed here. Lambda, this cosmological constant, is related to this mass square. When mass here is mass which is non-tachyonic, it is as it should be. And here also you see that amplitudes for the scale factor and for the theta field are also related to the mass to the power 4 in this case here. So what so we can see that we succeed to solve equations of motion in the weak field approximation for new field phi, which I call p-Adic matter, and we can solve equations of motion in the weak field approximation. It means instead of the field phi, we have now this theta. Yeah. So we succeed to solve it, and now. Okay, we are at the conclusion. I would like to point out that p-Adic strings are non-local, non-linear, non-Archimedean objects, which are in several ways related to ordinary strings. So they are very, very important also for the ordinary strings. And also the second point which I want to emphasize is that by slight modification in the Lagrangian for the p-Adic strings, bosonic p-Adic strings, which in fact describes a tachyon, one can obtain a scalar matter, which I call p-Adic matter, which makes sense, and it is not anymore, it is not a tachyon. And also we can put this new field in the universe, some closed universe, and to get also solution where this solution for the field in the weak field approximation is this expression here with sign minus plus, and then scale factor will be with sign plus minus. It means that that when we have this scalar field, which is decreasing with time, then we'll have exponential expansion of the universe, of the closed universe, and opposite when we have for the scale factor that it is contracting, it is related that our scalar field is growing. But of course, this growing cannot be larger because this is weak field approximation. Now, at the end, just I present here some references, starting with the reference of first reference related to p-Adic strings of Professor Dragovich, and then references which are the Freund, Olson, Brecke, Freund. This is a review article. Then Vladimir Volovich Zelenov book on p-Adic analysis and mathematical physics. Our review published on p-Adic mathematical physics, published in our journal p-Adic numbers, ultramathematic analysis and applications. Also, also paper Gubser and all related to p-Adic anti-de Sitter conformal field theory, Marcoli, Saberi, Stoica. Also to anti-de Sitter, Brecke, Freund, to non-Archimedean string field with Lagrangian. Yeah, in fact, this is. And Frampton Okada, Ghoshal Sen with tachyon condensation, Gerasimov, Shadashvili, Vladimirov wants some exact solutions. There are also some other people who consider the exact solutions or some solutions of p-Adic open closed strings. Also of the Wilson with his collaborators. Freund, Witten, Adelic string amplitude hour. Yeah, here is one my paper published in the Springer Proceedings of Mathematics and Statistics in 2013, where I started to consider, it is some initial paper related to p-Adic matter. And in this paper here, we presented the derivation of the equation of motion, which I presented in the previous slides. And at the end, thank you very much for your attention.
Okay, thank you very much. Some questions, remarks?
Yes, please.
Yes.
Thank you very much, Branko, for the very nice talk. It looks like in your solution for the cosmological model, you don't have a cosmological singularity.
Yes, here this is with bounds, one can say. In fact, we don't have, we don't have singularity.
Is it related with the fact that highest derivatives usually?
Yeah, we have non-local theory of gravity. This is in some sense modification of the Einstein theory of gravity. In fact, of the general relativity towards non-local gravity, and there are a lot of activity in the recent years about this approach. This is one of the perspective approaches to modify Einstein theory of gravity to solve problems with singularity and also with dark matter and dark energy, to get effects of dark matter and dark energy without dark matter and dark energy.
Okay, thank you.
So, okay, so if there are no more questions, so let us thank the speaker again.
Okay, thank you very much for your attention
Thank you,
again.
Branko.